Well, welcome everyone to another episode of Science of the Times podcast. It's a bit hot today, Simon, isn't it?
It is, even for me, and you tend to find it hotter than I do. But I have to say, I'm struggling a bit today.
Yeah, no, it's a bit warm. But what we're actually going to learn about today are some other planets where I think the temperature's even worse than it is today.
Sounds great. I mean, other planets, it's the dream, right? For all of us, I think, for scientists.
I have no desire to go to visit any other planet. Certainly not to live. I mean, it might be nice to pop over there, but I think the journey would be, as we'll hear, would be quite a long one.
I often think you're on another planet, though, too.
But so, what we're going to be talking about, our guest who will introduce himself in a second, we're going to be talking about exoplanets. Yes. So these are planets around other star systems.
Yes.
And I think it's only a few decades, we'll find out a bit more, since the first one was discovered.
Sounds fascinating. Shall we get him on?
Let's go for it. But before we do, remember, if you like this podcast, please like it, please subscribe, please share, and please tell everyone. And more details below.
Yeah,
but
sure.
let's get our guest on. So, Ray, would you like to introduce yourself?
Yes, hi, I'm Ray Pierrehumbert. I'm on the physics faculty at Oxford.
And you work on other planets. I mean, not literally, that's not your commute.
It's not my commute, no.
But how did you get into it? I mean, because you've got quite an eclectic background, actually, to get to the point of other planets, haven't you?
Yes, well, it's been a long journey. I started off my career at MIT working on just theoretical fluid dynamics, and then at some point I realized that atmospheres are fluids and have interesting fluid dynamics. I worked on that for a long time. I spent a long time working on things like global warming and past climates of the Earth, but at some point, once the first exoplanet, planet around other stars, was discovered, this opened up a whole new field, a whole new area for application of the basic physics we knew, but in very novel contexts. And so I jumped right on it.
So when was that? When was the first exoplanet?
Well, the first one was discovered roughly 30 years ago, and it's called 51 Pegasi b. The planets mostly don't have names of their own. They go by the name of the star. Sometimes the star doesn't even have a name. It just has a kind of a phone number. And then B would be the first planet discovered around that star, C the next one, and so forth. But actually, when the first planet was discovered, there wasn't a whole lot for people like me to do with it, because we didn't have the ability to say anything about what its atmosphere was like. It was only with later telescopes that we started to get into the planets where we could start to say something about what the atmosphere was like, what its climate was like. That's when I got really interested.
But these planets are a long way away, right? I mean, some of them.
Yes.
Well, all of them. I mean, the closest star
the
systems.
very closest one, it turns out, quite remarkably, the very closest star to Earth, which is Proxima b, which means close.
Yeah.
Proxima b, which is actually part of the Alpha Centauri system. So Proxima is a star that actually orbits around the two Alpha Centauri stars, but that's about 4 light years away. And it turns out that there is a planet around that star. That's the closest one. But traveling at the speed of light, as far as an observer on Earth goes, yes, it would still take you 4 years to get there, or more to the point, if there were an alien civilization and you sent them a phone call by radio or a laser or whatever, it would take 4 years for them to get it. But most of the other planets we look at are between, say, 20 light years to as many as 1,000 light years away. But it's only the closer ones that we can say something interesting about.
I mean, that's mind-boggling to me that we can say something about something.
Anything about it, yeah.
Yes, it's amazing what can be done with a fairly small trickle of data that comes back. Because when we see these planets, we actually, in fact, for the most part, we don't actually see the planet. What we see is the combined light from the star and the planet together. But because the planet is moving around the star, it introduces a time variation in the combined light from the star and the planet. And we can do a remarkable amount with that. Though in the last few years, it's become possible to directly image planets. We still get just one dot of light from the planet, but we do get a dot of light from the planet that's separate from the dot of light from the star. But that can only be done right now for very hot young planets that are far away from their star. Eventually, we'll be able to do this for more temperate planets.
So the first ways that some of these planets were detected, it was it not through the star actually wobbling? Was it
the very first? In fact, the very first groups of planets discovered were by what's called the radial velocity method. So a planet is a lot less massive than its star,
Yeah.
but still, since by Newtonian mechanics, the planet and the star orbit around their common center of mass, the star actually does wobble as a result of the planet. And that means when the star is moving towards you, the light is slightly shifted towards the blue. And when it's moving away from you, the light is slightly shifted towards the red. But it's a very, very small shift. And so it wasn't so much an aha moment that made this possible. It was the same old spectrometer, but at some point, the spectrometers got good enough that they could detect this very slight Doppler shift. At first, only for quite big planets, but now we can do it for smaller planets. But now the main way the technique that accounts for most of the planets in our catalog, and they're closing in on 6,000 now, is the transit method. If you're lucky enough that your planet passes directly in front of the starlight dims a little bit.
Okay.
And this started being applied some years after the wobble method.
Yeah.
It actually is much easier to do, and you can do it from outer space. We can't do the wobble method from outer space right now. So, but it's accounted for a lot of our planets. Now, you might think it's actually kind of, the planet's going around its star. It has to be lined up just exactly right for the planet to pass in front of the star.
Yeah.
But it turns out there are so darn many planets out there that even though only a few percent, if that, will actually pass in front of the star, we call that a transit, there's still tons and tons of planets that we can detect by the transit method.
And so what can we learn from this data that we get? What's the sort of extent to the information we can glean from all of this?
Yeah. Well, the most important thing we learn, which we learned from the very first planet, is that we're not, or as planetary environments, we're not alone in the universe. There was lots of reason to suspect that there were other planets out there, but we didn't know for sure. For all we knew, forming planets was really rare because, after all, when you form a star, almost all the material goes into the star. And so, was it a rare event when enough was left behind to make planets, or is it very common? And so up until 30 years ago, we didn't absolutely know that there were other planets out there. And now we know, in fact, just by the statistics of the planets we've discovered, it's very hard to make a star without making a couple of planets also. Right. And so just about every star that you see has one or more planets around it, except for some of the very, very massive, very bright stars, which may not have planets. But beyond that, there are other things that we can learn. But to me, the most remarkable thing was just knowing that, in fact, the universe is full of planets. It's chock full of planets everywhere you can see.
And so the planet is, sorry, Tim, just the planet is the leftover material from the process of forming the star.
That's right, yes. And in fact, it's also the leftover detritus from stars that blew up, because planets, the kind of planets we live on, and what we're made of are elements like carbon and oxygen and a lot of water, which comes from hydrogen and oxygen. Yes. But and the rock we stand on is made out of silicon and oxygen and various metals like calcium and magnesium. All that stuff did not exist at the beginning of the universe. Everything heavier than hydrogen and helium, essentially, was created in the first stars and in subsequent stars. And so in the material that makes a star, only 1% or 2% is the stuff we call dust, some of which is actually ice. Most of that is hydrogen and helium, which is what stars are mostly made out of. And it's what a big planet like Jupiter is mostly made out of. But the little bit left over makes the rocky planets that we know and love.
So I think in our solar system, over 99% of all the materials in the sun, I think that's right.
That's about right, yeah.
Wow.
So going back to detecting the other planets, the wobble, if that's true for other systems, that the vast majority, well over 90% is in the star. The gravitational pull of the planet must be relatively small, so the wobble must be tiny. I mean,
it is tiny. It's something like a fast trot. for the smaller planets.
Yeah, I mean, so the amount of movement relative to, because the Earth's moving as
Yes,
well. I
yeah.
mean, the changes that you're detecting in the data must be, pretty small in terms of the
Yes.
shift in wavelength.
Yes, I couldn't quote at you right now the how big the change in shift in wavelength is, but the sort of the sound bite is that the star is moving slowly enough that if you were a pretty brisk runner, you could keep up with it.
Is that right? Wow, that's what I wanted to.
Yeah.
Oh, wow. And so can we detect that from Earth, or do we have to use satellites in space?
Well, so the kinds of spectrometers that can detect this small shift in the color of the light, they're big. They need a very stable platform. They're heavy. They need a lot of power. And they also need a lot of photons, which means that you need a big mirror. And so right now, this kind of observation can only be done from large telescopes on Earth, whereas the transit method can be done with telescopes in outer space. And also the star has to be close enough in order to even have a chance to detect this very small velocity of the star. And so if it ever became possible to put these accurate spectrometers in space, that would be truly transformative, not just for discovering planets and characterizing them, but also in terms of finding the spectral lines that tell us what's in the atmosphere. I should say an important thing about this radial velocity method is that it gives us complementary information about the planet that we don't get from the transit method. From the transit method, we get the size of the planet relative to the star. And from theory, we know the size of the star pretty well. And so that gives you the volume of the planet. But the transit method, but the radial velocity method, the wobble method, tells us the mass of the planet. And so the sweet spot, the gold standard, is if you have both the mass of the planet and its volume, then you know its density. And since rock is much denser than water, you know whether the planet is made out of rock or water or something in between. But unfortunately, it's only a small fraction of the planets we know, like maybe 10 or 15%, for which we actually have masses.
It's remarkable, really, in a way that it's such fundamental physics.
Oh, yes.
It's
Well, that
nothing
is what
fancy
attracts
in
me
a
to
way.
it. It's the same physics our undergraduates here or at any physics department learn, but just by applying it to a new field, you get these remarkable new discoveries.
And so you were telling me a little while ago that you actually had, I think you described it as had time on the James Webb Telescope. So in other words, you got to choose where it was pointing.
Me and the team I'm on.
Of course not. You didn't just pick up the phone and say, "Can you move it a little bit left?"
Yes.
So how long does it take to? It hasn't been up there for that long. The James Webb Telescope.
It's about 3. We're going, I think, into the 4th year now. Yeah.
And how? What's the process of actually getting time on a process? I'm just thinking there's a few bits of the sky I'd like to look at.
Oh, it's a very drawn out and competitive process because the time on this telescope is very precious. There's only 24 hours in a day, and everybody is after time on this telescope for their own projects. And we in the exoplanet community are competing largely with people using the telescope for cosmology, because the telescope has also been transformative in terms of being able to look farther back, closer to the Big Bang, see the first stars and galaxies for the first time. But the process is that you get a team together, which is a mixture of people like me who do the theory and people who are observers who know the instrument characteristics in and out, and think about what is the interesting target, what is the interesting science question? What kind of targets are accessible? What stars are accessible, or planets are accessible to the instruments we have? And how do those targets address our science questions? Then you write a proposal. There's one competition per year. You put in your proposal, you sit, you wait, you hope. Mostly it gets turned down. I think they're down to maybe a 10% success rate on Webb proposals now. And then once and if your proposal is successful, then at some point you actually you actually get your observation scheduled, but you don't steer the telescope yourself. You don't. Well, there are some telescopes where ground-based telescopes where essentially once you get the time, you just type into your laptop and you tell it where to go, and you can look. And but not all of them. But that sort of thing does exist. But for the space telescopes, there's a very elaborate web form that you do not want to get wrong.
Yeah.
Where you put in the coordinates of your object, guide stars to help the telescope point in exactly the right place, and the time you're making your observation is very important, because you don't actually get a specific time down to the hour, second, or even day. And so if you're trying to catch the planet right when it's going across the star, you have to give it a list of all the times during the year when it does that.
Yeah.
And it had better be accurate. Otherwise, you come up with a nice, beautiful view of a star that tells you nothing that you can write a paper about.
We should probably take a break and go to our sponsors. When we come back, I think we'll find out a little bit more about the planets you've been studying and what those planets are like, and when are we going to find life on other planets and those sorts of things. But I mean, if you're enjoying the podcast, please please like, please subscribe,
and share
please
all
share.
the links. Yeah, lots and lots of links on lots of different formats. Spotify, Apple Podcasts.
Absolutely. I'm glad you can read that.
Hi, Tim. You're looking particularly snazzy today. What are you wearing?
I'm wearing a piece from a company called Grace and Garbo. And actually, you know a little bit more about them than I do, to be honest.
Yeah, you're right, I do. And
You're
as
the
you can
fashion
see,
queen. Yeah.
I'm also wearing a piece from Grace and Garbo. So this is a delightful knitwear outfit set up in Birmingham. What they do is they source knitwear, quality knitwear from all around the world. So it's vintage, one-off pieces, many of which they then hand embellish, like the one you're wearing today with its beautiful purple flowers. And so they're big on sustainability. Nothing goes to waste. Everything is sort of recycled and reused. And if you want to know more about them, then have a look at the link beneath this episode.
And thank you very much to them for supporting our podcast. I hope their sales soar.
Yeah, thanks a lot, Grace and Garbo. So welcome back. Okay, Ray, so we'd like to hear a bit more about the planets you've been studying. So, I guess the obvious question, the one we're both dying to hear about, is what's the most exciting planets you've studied?
Well, and they're all, it's like, what's my favorite child? No, they're all wonderful. Every planet is precious to me, especially the ones I've studied. I've been studying myself, but I'm especially excited about sub-Neptunes. It's a kind of planet we don't have in the solar system. It's considered to be like a miniature Neptune. That's a planet that has a lot of gas in it.
So Neptune's one of our outer lying planets.
Neptune is
an
one
ice
of our
giant,
outer
right?
planets,
Yeah.
right? It's a kind of planet that is called an ice giant. So Jupiter and Saturn are gas giants made mostly out of hydrogen and helium. And some people think that Neptune and Uranus are called ice giants because they're made out of ice. In fact, they're referred to as ice giants because the kind of atmosphere envelope they have is the sort of thing that would be derived from ice coming together to make a planet. It's mostly not there in the form of ice. It's mostly there in the form of various fluids. You can think of it as steam, or past a certain temperature, the distinction between liquid water and gaseous water disappears, supercritical. And the interior is mostly in that state. There is actually an exotic form of ice deep down in Neptune and Uranus called superionic ice, which is electrically conductive and which is a little bit like a fluid and a little bit like an ice. But we don't actually get that on our sub-Neptunes, which are not big enough for that really exotic form of ice. But the sub-Neptunes, and there's no reason we call them sub-Neptunes rather than sub-Uranuses, except, sub-Uranus, that sounds odd.
Well, we won't dwell on that.
We won't dwell on that. But it's a misnomer. They're called sub-Neptunes because they are smaller than Neptune but bigger than Earth, and they're low density, just like Neptune itself and Uranus. They're low density, but not such low density that they'd mostly be made out of hydrogen. and helium. But in fact, we've learned that most of these sub-Neptunes are closer to rocky planets than some people think, that they can easily be 90% or even 99% rock. But they still have an atmosphere that is a much higher proportion of the mass of the planet than for Earth. So even when we take Venus, which we think of as a planet with a thick atmosphere, 100 times the pressure of Earth's atmosphere, that atmosphere is only 1 part in 10,000 of the mass of the planet. So even 1% is a much more massive atmosphere than the atmosphere of what we consider to be rocky planets. But I'm enthusiastic about sub-Neptunes because they're kind of a fossilized version of what we think the Earth was like when it first formed.
Oh, really? So these sub-Neptunes aren't necessarily a very, very long way from their star. They're not out circling where Neptune would be here. They could be closer in. Is that
Well, they could be all over the place. The ones that we, they could be close in, they could be far out. People are still somewhat disputing how they're actually formed. But the ones we are able to observe so far are fairly close in. They tend to be hotter. The outer atmosphere tends to be hotter than Earth, or similar to Earth-like temperatures for a few of them in the outer atmosphere. But the reason I say that they're a little bit like what we think Earth was like originally is that we think, at least a lot of people think, that when Earth first formed and when rocky planets first form, they suck up a lot of hydrogen and helium from the gas disk that the stars and planets are forming in. And then they lose it later, and the hydrogen is lost easily, and then the heavier stuff like water, carbon dioxide, and so forth, stays behind. And so the Earth went all the way to losing all of its hydrogen and helium, and we kept just enough water for an ocean. But sub-Neptunes either started off with enough that they didn't lose it all, or they haven't actually finished losing it yet. We know sub-Neptunes, we can actually see the hydrogen and helium escaping in real time. Cool. And so it does give you a glimpse of what the early stages of planet formation might be like. Now, I should emphasize many of these sub-Neptunes, in fact, are as old as Earth.
That's
or
right.
Older.
Yeah.
And planets come in all different stages. And one of the things we try to do with the data we collect on sub-Neptunes is make whole models of how they got to where they are now from where they might have been originally when they were much more hydrogen rich. But they're exciting not only because they're like a fossilized version of what we think Earth might have been, but they have atmospheres that we've been able to characterize very accurately. They're smallish planets, so they have a lot in common with what might be habitable planets that we might discover later. But their atmospheres are much easier to characterize. We can tell whether they have carbon dioxide, whether they have water, and things of that sort.
Ray, if I'm being devil's advocate, how can we confirm that? How do you know that you've very well characterized the atmosphere of that planet?
Well, we can't go there, that's for sure. But actually, the main way we know is through having a lot of different groups banging away at the same data. So we characterize the atmosphere by looking at the colors of light that are either passed through the atmosphere from the star, the spectra, or that are emitted by the atmosphere, by the planet as a whole. And so we know this spectra. We know the characteristic signature, the intensity of light versus wavelength for all sorts of different species. And that we can get from laboratory measurements on the Earth. And so it's really mainly a question of have we done the statistics right to infer that we really think there's CO2 in this atmosphere. There's a famous example where someone who I won't name declared that a planet was teeming with light because they saw that.
I think this person was based at the other place.
At the other place, yes.
Cambridge, for our listeners.
And so there was a claim to have found a molecule dimethyl sulfide, which is produced by life on Earth.
This was quite recently, wasn't it? It was earlier
this was quite recent, yeah. But when other people looked at the statistics, the spectrum was in fact compatible with the flat line, and in addition, when other people looked at what other compounds could give you the same signature, was found that there were hundreds of other compounds
Right.
which could be produced abiotically, which give you the same signature. But even more basically, and this is not anybody's fault. With
Sure.
it's hard to do. You could criticize premature announcements that a planet is teeming with life. But the thing is, it's hard. People make mistakes. And one of the nice things about the subject of exoplanets is it's young enough that we have the freedom to make mistakes. Maybe we should be a little bit more reluctant to make mistakes, but people are friendly, and it's recognized that we're doing a hard thing. But so even when someone just say has discovered carbon dioxide in an atmosphere, in one of these sub-Neptunes, looking at the data some more, the indication of carbon dioxide went away. It's not to say it's not there, but it's just not statistically supported. But you can get more data, and so the trick is you get a detection, you think you're right, you have a certain confidence limit. And then other people look at the same data with different statistical methods. But then if it's interesting enough, you go out and get more data. And the more data you have, the more you beat down the noise and things of that sort. And so, for example, the sub-Neptune I'm especially working on, called TOI 270D, our detections have held up pretty well. We see water vapor, we see carbon dioxide, we see methane. We don't see any ammonia, and this tells us something about what we think is going on deeper in the atmosphere. And a lot of people have reanalyzed the data, and it's holding up pretty well.
Any nitrogen at all, or no nitrogen?
Well, now this is tough. So nitrogen, N2, which makes up 80% of the Earth's atmosphere and is essential for life as we know it. Nitrogen itself doesn't have any spectral features that are useful. It doesn't have spectral lines. In fact, all diatomic molecules made of the same two atoms are free of spectral features. They do have
including
some,
O2 then?
What?
Including oxygen?
Oh, oxygen,
helium,
yes.
right.
Although oxygen does have spectral features in the ultraviolet and visible that people look for, but it doesn't have infrared transitions, which is what James Webb can detect. Doesn't have infrared spectral lines. Now nitrogen actually is the most common greenhouse gas on Titan, a very cold planet, but it's not because of spectral lines. When nitrogen is colliding with itself, for a while it acts like a more complicated molecule and it can be absorbing, but it's very hard to use that feature because it's a very fuzzy feature, and so it's hard to. So we would love to know about nitrogen because, especially for habitability, nitrogen is at the basis of all biology, as much as carbon, and we don't really know much about how nitrogen is delivered to planets. Nitrogen is incredibly common in the universe. It's one of the things stars make really well. But the Earth is incredibly depleted in nitrogen relative to what the sun is made out of, which gives you an indication of what the Earth was originally made out of. And we don't really know, how did we get so little nitrogen and not zero? But we do try to infer the presence of nitrogen by looking at compounds we can detect, hydrogen cyanide and ammonia.
Yeah, of course.
HCN is especially interesting because it is one of the building blocks of prebiotic chemistry. It's one of the main ways that the people studying chemistry of origins of life get nitrogen into the biological systems. It's ironic because it's just horribly poisonous to complex life as we know it.
So, I mean, we haven't discovered life on another planet yet.
We haven't even discovered habitable planets yet with atmospheres.
Right, but if there was life on another planet that you were looking at, would you be able to detect it?
Well, so this is the perpetual question, and so the main way we think of detecting life on another planet is through the gases that it might produce in the atmosphere. So under some circumstances, for example, if you see methane in an atmosphere at a certain concentration, that might be an indication that there's life. But not all methane detections would mean life because there are lots of ways of making methane without life. And so you have to find methane in a circumstance in which it's destroyed so fast that you need a biological source to keep it up. And so it's always going to be dicey because there's a question, have I really thought about all the non-biological sources of my biosignature gases? And so, for example, in this famous example of dimethyl sulfide, if they ever do detect it, it still won't be an immediate signature of life, because we know at least two different non-biological ways of making dimethyl sulfide in a sulfur-rich atmosphere. And so determining whether the DMS you see is an indication of life or not will always be difficult. And of course, oxygen is of interest because it's produced by photosynthesis, but oxygen can also be made abiotically, and so we're always grappling with the issue of false positives. Ironically, one of the most uninhabitable planets that I work with, the lava planets, which are so hot that they have a permanent lava ocean on the day side, those molten rocks actually produce a lot of oxygen, because the oxygen that's bound in the silicate rock, which is made out of SiO3 and similar things, that dissociates and you get oxygen. And so no one would think that on a planet with a surface temperature of 2000 Kelvin, oxygen is going to mean life. But that just makes the point that whenever you see a biosignature, the context is essential. You have to ask whether this is a context in which you conceivably could have life. At least life as we know it.
I guess it would, if you had a combination, you had oxygen, you found nitrogen, you found phosphates or something, it would be an indication that it's a stronger.
So combinations help. So if you, since oxygen destroys methane, if you see oxygen and methane together, which is actually hard telescopically, but with the current generation, but if you see oxygen and methane together, that generally means you need a very strong methane source in order to fight the oxidation, the destruction of methane by oxidation and so forth. But one of the tougher things is that we know Earth had no oxygen in the atmosphere for its first 2.5 billion years or so, and so and it could be quite rare for life to evolve the ability to produce oxygen from sunlight, and so finding clear biosignatures for the pre-oxygenated form, which might be the stage most planets are out there are in, that's tough. That's tough. So
detecting life's hard. We're running out of time, so just a couple more questions. So detecting life's going to be hard. You know, one of the things that people argue about Earth is, you know, we're obviously a planet that can support life. We have a sort of reasonably, pretty stable orbit. We don't go too far from the sun. We don't go too close to the sun. We spin at the right speed. We have a magnetic field. All of these things that people talk about being important potentially for life. We have a moon. Are we anywhere near, you know, in the next decade or so, are we going to be able to work out how, the orbits of some of these planets? Are we going to work out whether they have moons, whether they have whether they have magnetic fields?
Well, we already know the orbits. The orbits are one of the things we know best, and we know it for a long time. And so systems with very circular orbits, they're really common. So we're not unusual in that regard. And magnetic fields are hard to detect, but I think they're oversold as an essential ingredient.
They don't help us keep our atmosphere?
So, you can look, Venus has no magnetic field.
And it's
got plenty of atmosphere. And actually computer simulations indicate that magnetic fields actually sometimes can accelerate the loss of an atmosphere by focusing particles into polar regions and then helping to channel all your atmosphere that's trying to escape velocity in the polar regions and so forth. So it's not so clear that magnetic fields are the make or break thing. It's really atmospheres and delivery of things like nitrogen that are the make or break thing. And where we're hampered right now is the planets that we can characterize best are planets around low mass stars, these reddish small stars. And these kinds of stars are incredibly good at producing the energetic ultraviolet that is really good at blasting away atmospheres. And so it's much harder to detect with current technology and characterize planets around sun-like stars, which are not so good. So at blasting away atmospheres. Now the low mass stars, I was hoping that we would find lots of atmospheres around these M-star planets, around low mass stars, because they're by far the most common star in the galaxy, in the universe, almost certainly. G stars like the sun are less common, although they're still
They're
fairly
not that
common.
unusual, though.
They're not that unusual. But right now, a planet that is far enough to have liquid water, if it's too close, the water just evaporates and goes into space. The planet that is habitable, in the habitable zone, it has to be pretty far out, just like we are. And so if you have a 1-year orbit, your chances of actually detecting a transit are small. Actually, the chances the planet transiting at all are small. And also the chances of being able to measure the mass by the wobble of the star are small. And so our current generation of telescopes has a really hard time finding things around sun-like stars or characterizing them. Well, the things we can find are the wildly uninhabitable ones, like the lava planets, which are close in. So,
we're going to need a bigger telescope.
but I'm not giving up hope on the planets around low mass stars. Maybe some of them have a hard time holding atmospheres, but there are a lot of planets out there, and it's still early days for surveying the habitable zone planets around low mass stars.
Simon, do you have one last quick question? Or
sort of. So, what's the next sort of the thing you're working on now that excites you the most?
Oh, the thing it's both our new lava planet observations, which tell you what a rocky planet is made out of, because it's easier to tell what a rocky planet is made out of if you evaporate the rock into the atmosphere where you can see its spectral lines. If it's just sitting there, it's got kind of wimpy spectral features that are hard to see. And so that's really exciting. We're getting good atmospheric characterizations, and they have really amazing atmospheres, because some of them, the ones that have just rock vapor in the atmosphere, they have supersonic winds. They go from the day side, then you get basically beach sand snow that comes back down when the atmosphere goes into the colder part of the planet, and they just have amazing possible characteristics. But then in the sub-Neptunes, we found that where the rock meets the gas of the envelope or atmosphere, it's hot enough that the rock is molten. And so you have these fascinating chemical interactions which are just beginning to work out between the gas and the rock. And you can actually manufacture water at this interface by reacting hydrogen with minerals. Oh, wow. So it makes its own water. This is one way Earth might have gotten water. So I'm incredibly excited about this. These are things that we have data on right now, and learning about the time evolution of these things. I in the future, I'm really interested to see which rocky planets have carbon dioxide and how much, because that gives us a test of the processes that kept the Earth habitable over the last 4 billion years. But we don't have examples of those kinds of planets yet, but I hope we get them.
Well, Ray, thank you very much for joining us. That was absolutely fascinating. And we'll put a link to a couple of your recent papers below as well.
Yeah.
And so listeners, remember to like, to subscribe, to share.
Yeah, tell all your friends.
Tell all your friends. And thanks to Grace and Garbo, our sponsors.
Yeah, absolutely.
So, Simon, that was fascinating.
Honestly, it really was. I had no idea we could get that much detail about something so far away.
I know, just from relatively small numbers of pixels in some cases, and wobbles and movements of suns and stars elsewhere. Just incredible.
And just the stuff Ray was saying at the end, I guess we may discover new chemistries, right? New reactions and new reactive pathways.
Well, I know. I mean, being able to study molten rock on Earth is probably hard. It might be easier to do it through telescopes miles away. But no, I mean the universe is so vast, and there's so many planets out there. I think over 5,000, nearly 6,000 exoplanets have been discovered. That each is a little bit different from the others. So Some types are more common than others. But yeah, I'm sure you're right. I think there's a load of chemistry to learn.
And just the idea of all these different topologies on these planets, right? These different landscapes and this idea of these winds blowing around that are hot and cold, and it's just mind-blowing. It's like Star Trek becoming real.
It is, except it's kind of, I just wish they found a way in which they could detect life on other planets.
You're gagging for this, aren't you?
Other than a radio signal of someone saying, we're out there and we're coming to get you.
There'll be some crazy green alien somewhere, Tim, and it's going to come and find you first.
No, and I was wondering, because you can see the light reflected from a planet. If you were 20 light years away looking at Earth, would it look a little bit green and blue? I don't know. We should have asked him that. Anyway, we'll have to get him back on it.
Yeah, we'll definitely get him back.
Yeah. Fantastic. Okay, well, have a good week, Simon.
Yeah, you too.
Yeah, okay.
Bye.
Bye everyone.
Bye.